Good morning, everyone. In this presentation, you will be introduced to research paper on visual question answering framework for satellite image perspective, written by the team of authors including Milind Rane, Siddharth Borge, Mandar Prathamesh Jyotika, and myself Nikhil Rane. Our affiliation is with Vishwakarma Institute of Technology in Pune, and our paper ID is 1785. Moving on to the next slide, let me give you an outline of what we will cover today. Our presentation is divided into several sections including introduction, literature survey, problem statement, dataset, proposed architecture, experiments, and then results. Now let's begin with the introduction. So firstly, what is visual question answering or VQA? Visual question answering is a subfield of computer vision that involves answering natural language questions about visual data. Its potential application in various domains including healthcare, autonomous vehicles, and robotics thus make it a highly promising field. So what's the need of it in geospatial domain? The satellite imagery is valuable source of data for various applications, including urban planning, environmental monitoring, and disaster management. However, these traditional image analysis techniques have limitation in terms of their ability to extract useful information from satellite imagery, especially when it comes to complex tasks such as object recognition and scene understanding. This is where the VQA comes in. By combining computer vision and natural language processing techniques, VQA enables us to extract more meaningful insights from satellite imagery. With VQA, you can ask questions such as what is the land cover type in this area or how many buildings are in this image and receive accurate actionable answers. During our literature survey, we explored various datasets for computer vision and remote sensing visual question answering. Some of the datasets we examined were FloodNet, AI2D RST, HerMike VQA, and RSVQ XBin. To address the challenges of VQA tasks, different models and techniques were proposed, including segmentation, object counting, and co-attention. While doing literature survey, we came across several methodologies such as baseline models, discount net, multimodal attention-based system, MCB, top-down and bottom-up attention mechanism, neural network, convolution neural network, multi-level visual feature learning, prompt RSVQA, and VILT. Coming to the problem statement, the aim of this project is to create an AI-based visual question answering system for human interaction with satellite imagery data. The proposed system will allow user to input the image and ask natural language question, and the system will give the most effective answer. User can ask the questions for counting problem, condition recognition, and yes/no type questions based on the image provided. For this research, we use FloodNet dataset. FloodNet is a flood disaster dataset created by Mariam that includes various types of images and natural language question answer pairs annotated with specific topics. The pre-processed dataset has 4500 question answer pair covering 1400 images categorized into simple counting, complex counting, road condition, overall image condition, and yes/no type questions. Our VQA methodology consisted of three parts: the visual part, language part, and prediction part. The first part is to extract visual image features. For that, we use ResNet 50 architecture. Then, the second part included extracting text intent features. For that, we utilized Roberta transformer architecture. To fuse this feature from both the language part and visual part, we used methods such as concatenation, multiplication, and element-wise addition, and hence creating a new feature vector that captured the interaction between visual and textual data. Finally, we used the trained model for classification purposes. We evaluated different combination strategies and visual encoder models using pre-trained encoders, ResNet 50 for visual and Roberta Large for quotient text encoding. We froze the model layers and used the Adam optimizer in order to leverage the pre-trained models and combination of strategies, and hence we achieved state-of-the-art performance while keeping the computational requirement as low as possible. Freezing the layers of the pre-trained encoder model reduced the training time and computational requirements. Coming to the results, we have reviewed simpler combination strategies for VQA using the architectures for vision and language encoders. You can see that the results show that ResNet 50 gives overall better accuracy of 7% over the FloodNet baselines for simple count and complex count prompts, whereas the ResNet 50 with feature concatenation performs better than baselines by 1.7% better for condition recognition prompts, and VILT gives around 3.4% improvement over the baseline models. These are some results of the UI developed for output testing phase using Streamlit and FastAPI. Here, users have provided with simple counting question. Here, The user have provided with some complex counting question like how many residential buildings are there, and the AI outputs the answer as 20. There is also one yes no type question where the user asks the question like does this picture contain football stadium, and the AI outputs answer as yes. Coming to the future scope includes exploring other visual encoder models, investigating real-life applications, evaluating the achieved results on large-scale dataset, deploying as an application for field workers, emergency responders, or the general public, and also the integration of the audio part for the visual impaired people. So, in conclusion, our research show that using pre-trained models to combine visual and text information for VQA with satellite images results in effective and efficient solutions. Our top model achieve high precision while reducing training and inference time. This represents a significant step towards cost-effective VQA solutions. These are some of the references we have referred for our research. Thank you.